Okay, so for those of you who may not have been able to make the review session on Wednesday, I want to give you an opportunity to check your answers and listen to rationale behind some of the answers. Okay, so we had to select all the true statements. It was just mainly making sure that you feel comfortable with some of the definitions that we've used over the year. So chlorine and bromide cannot have the same number of electrons. They're different elements. They're in different columns. They have different numbers. Electrons, iron 2 plus and iron 3 plus are the same identity. The number of protons determines the identity, so B is definitely correct. Anions carry a negative charge. Atoms that gain an electron become an anion, so that's wrong. Copper plus and copper 2 plus are going to have the same number of protons but different numbers of electrons. And yes, potassium plus is formed when a potassium atom loses an electron. So we should have picked B and F. Here's the case. Okay, we want to look at hydrogen atom and which transitions release energy. So keep in mind our model for hydrogen looked like this. So we're looking at N equal 3, 1, 3, and 7. Of course, the other even numbers are present, but we're not really interested in those right now. And what we're saying is if you go from an N equals 1 to N equals 3, the potential energy increases. You're separating charges of different charges, right? They're different signs. Potential energy increases as you separate them, so that's going to require energy. While going from N equals 7 to N equals 3, they get closer. That releases energy. Potential energy decreases. So energy is released when you go from N equals 7 to N equals 3, or as the electron gets closer to the proton, and it increases when you separate the charges. Okay, so that would be, answers would be B and C. The release of energy is N equals 3 to N equals 1, and N equals 7 to N equals 1. Okay, question 3 is about the determining the empirical formula versus the molecular formula. And in general, you're not going to be asked a specific question mathematically on how to find it, but you should be able to determine empirical and molecular formulas and at least explain in how they're used. So looking at the elemental analysis, we first determine what are the mole ratios, right? Because that's really important. And we see the mole ratios for a 100-gram sample is 4.5 moles to 9.15 moles of hydrogen to 2.25 moles of oxygen. We divide by the lowest number, and we get the ratio of to one oxygen atom, we have 2 carbons and 4 hydrogens. So we can now write the empirical formula this way and get the empirical mass, which is 44. They give us the molecular mass as 132. That's 3 times our empirical formula, so we have to multiply each of the coefficients of the atoms by 3 to get the molecular formula, which would be D. So again, this calculation isn't so important per se, but you should understand the connection between empirical and molecular formulas, and that all of the units are done with mole ratios and atom ratios. So this is a quick balancing reaction, so let's just make sure you have any questions. So we have a fairly complicated reactant with iron and oxygen, so we just put a 1 there. So we balance 2 irons. We need to put 3 halves here in front of CO2, so when multiplied by 2 we get 3 oxygens, which is what we have. And then we put 3 halves carbon. This is in fact balanced, but if we wanted to have only integers, we would multiply the whole thing by 2. We get 2 Fe2O3 plus 3 carbons to make 4 Fe solid plus 3 CO2. That should be balanced. You have the same number of irons on both sides, oxygens and carbons, which looks like we do. We have 6 oxygens on each side. That answer would be D. Question number 5 says if we're looking at this balanced chemical reaction and we're told that the iron 3 plus O2 minus ionic interaction is more stable than the carbon double bond O, then what we're really saying is that the potential energy here, that the potential energy is higher for C double bond O, which is a product, then the ionic species and the reactant. So we could write the potential energy like this: less stable C double bond O, more stable Fe2O3. We have an endothermic reaction. Delta H is greater than 0. Delta S is greater than 0 because we have solid plus solid in reactants making solid plus gas. Number of configurations and entropy is increasing, so we would have a positive delta S. And of course, if we have delta H greater than 0 and delta S greater than 0, we should be prepared to draw the corresponding delta G versus T curve and K versus T curve, which we see that the reactant favored at low temperature, product favored at high temperatures. We should also be prepared to draw the H versus S curve, which is up in the top right corner. And because delta H and delta S have the same sign, the R reactants and products lie along the diagonal. And since it's endothermic, products are in the top right quadrant. We should pick B. Okay. So it's really important to evaluate, make sure you can evaluate potential energy based on information given, and then assign the trends with temperature. Okay, so which plot shows steam entering a cold chamber and converting to ice? Okay, so this is about potential energy changes. So the biggest change in potential energy occurs going from gas to liquid. So that means that we're looking at the different choices between A and C, which is the big potential energy drop that occurs from gas to liquid. The other two have show the largest change going from liquid to solid, which is not what happens. And then based on the choice between A and C, we see that we start at a high temperature and then we go down in potential energy. We're releasing it into the surroundings, which is what we would expect. So we would pick A. Gas to liquid to solid means potential energy is decreasing. Right? That's going to be the opposite. If we're heating ice to a boil, then we expect that we would have to provide this energy. Potential energy should be increasing, and we would expect C. So 6 and 7 are kind of a pair. You just want to make sure the biggest change observed is when you're going for separating liquid to gas. Okay, so using the plot here, which has the highest velocity, so what we have to do is to look at, just keep in mind that at a given temperature, the kinetic energy is going to be proportional to temperature. But this kinetic energy has to be shared between the mass and the velocity. So as the mass goes down, the velocity goes up. So what we have to do is take a look at the average mass inside the two different phases. And if we do that, one might be tempted to say, oh, the gases are the lightest, right? So because they're in the gas form, but we have to keep in mind that those gases are made up of nitrogen, oxygen, and water. And on average, those are going to be slightly heavier than water, right? Because water is 18 grams per mole, nitrogen is going to be, well, oxygen's 32, nitrogen's 28. So in the gas phase, which we have mostly nitrogen and oxygen, is 28 grams per mole. Water is only 18. So on average, the liquid phase is lighter. If it's lighter, it's moving faster. So we would expect the liquid phase to be moving faster, which we would select B, right? So just keep in mind that's going to be related to the fastest moving particles, not necessarily the phase. So look at the Peck diagram, nitrogen and water, and so the idea is, what would that look like? And so although it's not going to be very important for the final, just keep in mind that as you heat up dissolved gas and water, that the unmixed state, or the gas separating, becomes more favored. The mixed state particles are closer, have lower potential energy. Versus sugar, which is our common experience, is that you have to heat water up to dissolve more sugar. The mixed state, because it has hydrogen bonding just like water, has higher configurations. And so we see two different Peck diagrams and two different responses, which would be B. Okay, so here's a molecule, and we're asked to determine the molecular geometries at points 1, 2, and 3. Looking at these, we see a nitrogen with a lone pair, carbon, and oxygen with 2 pairs. So we have bent, tetrahedral, and trigonal pyramid. All of these represent the electronic geometry of tetrahedral, meaning 109 degrees, but because of the lone pairs, some of the angles might be slightly lower than 109. So we would pick B. Next molecule has 2 different environments of oxygen atoms. In one, we have the tetrahedral electronic environment or molecular bent versus the trigonal planar environment. Here we see 120 degrees for the trigonal planar versus 109 degrees, or slightly less than 109 degrees because of the lone pairs. And we would pick D. Question number 12, we're asked about a transition that occurs at constant temperature, but the pressure changes of liquid to gas. So we're looking at the pressure temperature phase diagram. So we're at a liquid, and we're going to go to gas at constant temperature, which means the pressure must decrease at constant temperature. And we must go from a liquid to a gas. So we would pick D. That's the gaseous form as a product, and so we would pick D, liquid to gas, and pressure decreasing. All right, so this is looking at the this is at the particle this is the particle representation, submicroscopic representation of particles, and you should be able to balance reactions and find the limiting reagent. So looking at this, we just do the accounting. There's 4 NO particles plus 5 H2 particles reacting to make 4 water particles plus 2 nitrogen particles, and there's an extra H2 particle. So we can subtract the hydrogen that's unreacted from the initial reactants, and we get 4NO, 4H2, making 4H2O plus 2N2. These have a common multiple of 2, which we can divide out, and we get the answer 2NO plus 2H2, make 2H2O plus N2. So that would be the answer, would be D. The limiting reagent is clearly going to be the substance that is ultimately fully consumed in the reactants, and if there were more, we would make more product. And that's the case for NO. NO is a reactant, but it completely disappears in the products, unlike hydrogen, in which there's an extra hydrogen particle present in the products. That's in excess, so we would pick B. Here's a chemical reaction where we have the quantitative values for, so we can calculate delta H and the activation energy. See, this is 25 and it's going to 50. The potential energy is increasing, so we would expect delta H greater than 0. Endothermic. The activation energy is going to be measured from the reactant's potential energy to the maximum of the transition state. That would be, it would be 75 as it goes up to 100 from 25. So we would expect the answer to be B. In question 16, we have a mechanism shown here, 2 steps, and we have to keep in mind that step 1 is exothermic, but step 2 is endothermic. So we want to make sure that we can assign the state that has the mechanism that has this characteristic, and we see that the activation energy for the first one and the second one, if we evaluate it, the second step of activation energy is higher than the activation energy of the first step, which means that step 1 is fast and step 2 is slow. So we need something that has step 1 fast, step 2 slow. Step 1's exothermic, but step 2 is endothermic, and if we look at that, that means the choice is between B and C. But since A going to 2B means that A is breaking apart, in B that means it's being endothermic. Endothermic is not what we have. We have exothermic, 2 particles making 1, and C is much more consistent with exothermic behavior. And second step, A breaking apart into 2 to make endothermic. So we would say that the best answer here would be C. has the right activation energy ordering, and it has the right potential energy ordering. So just make sure that you pay very careful attention to the formulas in terms of assigning the mechanism. Question 17, we have a two-step mechanism, slow and fast. That means so step 1 is slow, meaning that the reactants are going to be part of the rate law. We can write the rate law straightforward. Rate is going to be K equals A times B. It's not going to be A squared times B because it's not the overall reaction. It is the molecularity of the slow step. Slow step is A times B. But that means we also are responsible for rate versus concentration with A or B. But with A, we see it's first order in A, so we see first order behavior. Keep in mind this plot is assuming that B is held constant. Concentration versus time for first order should show a nice exponential decay. Okay, so using this image, what would be the formula, or what would be the image, most reasonable image for nickel fluoride ionic substance? So keep in mind most ionic substances are solids at room temperature, and they do not form molecules. So that's why A would be wrong. What we expect is that there would be a regular array of nickel and fluoride ions in a 2-to-1 ratio. Best choice for that is going to be B. It's tempting to write it as a molecular as if they're sharing electrons, but it's not the case. A is wrong. Question 19 is, so we have to evaluate the chemical reaction, determine is delta H greater than 0, is it greater than 0 or less than 0, to find out if we have reactant or product favored. So AA bonds have higher potential energy than AB bonds. We see that the products have AA bonds, so we can write the products as having higher potential energy than the reactants. They also have higher entropy because there are 4 molecules of gas versus 2 molecules in the products instead of 2 molecules of gas in the reactants. So this is our curve, and as temperature goes up, we expect products to be favored. Here, so if we're in a product favored, then we would expect B, which is that we're making more products than reactants at some time, T, when equilibrium is established. B. D is wrong because that's showing a reactant favored chemical reaction in which there's just a little bit of product made and most of the reactants remain unreacted. All right, for the last question of the review, it's an acid-base question. So we look at the 50% mark, and at the 50% mark, pKa equals pH, right? That's H3O plus equals Ka because the concentration of H3O plus and its conjugate base, it cancels. And so we get pH, so if pKa is 10.2, then pKb is 14 minus 10.2, which is 3.8. That should give us D. So just keep in mind these graphs, really important, the relationship to pKa, pH, and pKb. All right, so good luck, everyone.